One of the most important continuous distributions is the normal distribution. The normal distribution was defined by Quetelet. Quetelet was a Belgian mathematician who obtained his PhD at Ghent University. While doing research on the body mass index, he noted that there was a very specific form of a histogram, and he put this form forward as the ideal histogram. So he would place this as an ideal histogram for the representation of the data. So he would say this is the normal shape of what my data should look like, hence the name normal distribution. What is this normal shape? Well, it is a bell-shaped distribution. It is symmetrical, and it is what we use as a reference distribution. So when we say that another distribution is heavy-tailed, this actually means that the tail of that distribution is heavier compared to the tail of a normal distribution. Since every distribution is defined by its density function, also here it is sufficient to define the density function. The density function which can be seen on screen. So it is 1 divided by sigma times the root of 2 pi times the exponential of x minus mu squared over 2 sigma squared with a minus sign. In this formula, mu corresponds to the population mean, so the mean over the entire population, and sigma is the standard deviation in the entire population. Of course, these are theoretical concepts, so mu and sigma are unknown, usually since they are parameters of the population. Research has shown that a lot of biological data can indeed be approximated by a normal distribution. Examples are body weight, the logarithm of the glucose level in the urine, bone density, and so on. It therefore is really a representative distribution. It can be seen as a normal distribution of a lot of biological data. For notation of the normal distribution, we will use a script n, so a curly n, with the two parameters mu and sigma squared. So we will use the convention to write down sigma squared, the variance, but pay attention, some others use mu and sigma. So if you are reading a paper or a book, always be very careful on what they are giving. Is the value, the second parameter, does it correspond to the variance or to the standard deviation? You always have to check that, but in our course we will use the variance. And then there is also a very special case, which is the standard normal distribution. Standard normal distribution is a normal distribution with mean equal to 0 and standard deviation equal to 1. This distribution gets its own naming conventions. A variable which is standard normally distributed will be denoted by the capital letter Z, and the cumulative distribution function will be denoted by capital Phi instead of capital F. So we said that a normal distribution is bell-shaped and symmetrical, and so a standard normal distribution is the same. It is bell-shaped, it will be symmetrical, and it will be always symmetrical around the center. For a standard normal distribution, the center is 0, and so the y-axis will be the center of the symmetry. Since the distribution is symmetrical, we can also write down the following property. Phi of minus z is 1 minus phi of z. We know that phi is the cumulative distribution function, so it corresponds to the area below the curve to the left of the value between the brackets. So phi of minus z would be the area indicated in green. Since it is symmetrical, z and minus z are at equal distances from the origin. So the area below the curve to the left of minus z will be equal to the area below the curve to the right of z. So phi of z is the area below the curve to the left of z, indicated in red. And since we then also know that the total area below the curve is equal to 1, the property follows immediately. From the graph of the density function, it also follows immediately that phi of minus infinity is 0, because there is no area to the left of this value. Phi of plus infinity is 1, and phi of 0 is 1/2 due to symmetry. And then the cumulative distribution function corresponding to a standard normal distribution is the following. On this plot we see that phi of minus infinity is indeed 0, and on the right hand side we have phi for plus infinity is 1. So these are the two asymptotic values on the left side and on the right side. Please note that the blue curve will never attain 0 or 1 itself. These are asymptotic values, which means that at minus infinity the curve becomes 0 and at plus infinity the curve becomes 1. But in all other values it is going to 0, it is going to 1, but it will never be equal to 0 or 1. And furthermore, we also see that the value in 0 is 1/2. 1/2 because it is a symmetrical distribution around the origin, if you look at the density function. So half of the probabilities is to the left of 0, half of the probability mass is to the right of 0. So a normal distribution is characterized by two parameters, the mean and the standard deviation. Furthermore, there is a very important property for normal distributions. Namely, if we have a variable which follows a normal distribution, then any linear transformation of that variable will again follow a normal distribution. So assume we have a random variable x which follows a normal distribution with parameters mu and sigma. Then the linear transformation ax plus b will follow a normal distribution but with different parameters. So the new parameter for the mean will be a times mu plus b, so it also follows the same linear transformation as the variable itself. And the new variance will be a squared sigma squared instead of sigma squared. These new values of the mean and the variance can easily be computed taking into account the formulas for mean and variance. So the theoretical mean, or the expected value, has as formula 1 over n times the sum of the xi's. The theoretical variance, it's very similar to the sample variance, has the formula given on screen. So if we want to calculate the expected value, for the transformed variable, we just plug this in. So it gets the sum, 1 divided over n times the sum of a xi plus b. Then you just apply basic rules for a summation. So you take out a, which gives you the first term, and you get the sum of all b's. So what you have in the second term is n times b actually, because you have n times the same value and then you divide that one by n. And so you end up with a times mu plus b. For the variance you do the same thing. So you plug in ax plus b, you plug in into the formula, so you have to change both the variable x by ax plus b as well as the mean mu, which is now the mean of the transformed variable, so a times mu plus b. You plug this in, you apply basic rules, so you take the corresponding terms together, the ones with a and the ones without a, so b will cancel out, it will be b minus b. Then you can take out a, becomes a squared over n times the sum of xi minus mu squared. And this is actually just the variance that we had before, so you had a squared times sigma squared. Why is this property important? It's important because it allows us to bring back any normal distribution to a standard normal distribution. So by applying a simple linear transformation, any normal distribution can go to a standard normal distribution. Which transformation do we have to apply to go to a standard normal distribution? This can easily be calculated just by thinking about what we want to obtain. So we want that the new mean is equal to 0. So a times mu plus b has to be equal to 0. And on the other hand, we want that the new variance is equal to 1. A squared sigma squared has to be equal to 1. This means, for starters, that a has to be 1 divided by sigma. If we then plug in the value for a, 1 over sigma, into the first formula, we obtain that b has to be equal to minus mu divided by sigma. And thus the linear transformation that we need will be 1 over sigma times x minus mu over sigma, or it is x minus mu divided by sigma. Using this property, we can calculate probability x smaller or equal than x for any normal distribution. And this is done in two steps. First, we standardize the normal distribution, so we bring it back to a standard normal distribution by subtracting the mean and dividing by the standard deviation. And then we look up this value in a table. So there are tables created with all the values for the probabilities z smaller or equal than z, so with all the values for the cumulative distribution function of a standard normal distribution. The table with these values can be found on page 353 of your course notes. As you can see, in the table are only the positive values of x. Why? Because the negative values of x can be calculated using the symmetry formula. So phi of minus z is 1 minus phi of z, you can apply this to find the same values or to find the probabilities for negative values of z. So to find the probability of an interval for a variable which follows a normal distribution, you only need to know the values over the standard normal distribution. So assume that x follows a normal distribution with mean mu and variance sigma squared. Then if we want to calculate the probability that x is between a and b, what we do is we first apply the transformation. So we apply minus mu over sigma to every term in this inequality. Then we know that x minus mu over sigma is equal to the variable z, which follows a standard normal distribution. And then you can just apply the fact that the probability for an interval is the probability for the upper value minus the probability for the lower value. So you end up with phi b minus mu over sigma minus phi a minus mu over sigma. And so you look up those two values in the table for your cumulative distribution function of a standard normal distribution. You plug them in and you know the final probability that x lies between a and b. With what we know so far, we can now try to see what the most likely values are. So we could construct an interval that contains 1 minus alpha percent of the most likely values. Such an interval is called a reference interval. Let's start by introducing the following notation. Z1 minus alpha will represent the 1 minus alpha percentile. So it is the point for which that 1 minus alpha percent of all the data is to the left. So the probability that my random variable z is smaller than this value z1 minus alpha is exactly equal to 1 minus alpha. Or when we look at the density function, this means that the area below the curve to the left of the point z1 minus alpha is equal to 1 minus alpha percent. So for example, if we look at the value z.95, this is the 95% percentile. It means that the red part in the graph corresponds to 95% of the data. If we then want to construct an interval which contains 95% of the data, then we have the following. For such an interval, we know that the interval has to contain 95% of the data, but an interval has to be symmetrical. So we are looking for a symmetrical interval around 0. And so it means that if we look at the density function, it means that to the left of the interval, we have to have 2.5% of the data, half of the 5% which is not in the interval. And also to the right, we have to have 2.5% of the data, half of the data which are not in the interval. So we want to find an interval that contains the 95% most likely values of my random variable z. Or if we want to write this down, the probability that z lies in this interval has to be 95%. Now, what will be the boundaries of this interval? Basically, what we want is that to the left of the interval there is 2.5% and to the right of this interval there is 2.5%. So the area above this interval contains the remaining 95%, so the most likely 95% of the data, the ones in the center. What remains to be done is determine the boundaries of this interval. So we have to determine these 2 points. The left one is the easiest. We know that 2.5% of the data lies to the left of this point. And so this is nothing else than the 2.5 percentile or z0.025. For the right endpoint, we can make a similar reasoning. If we look at this point, we see that 97.5% of all the data lies to the left, and so this is nothing else than the 97.5 percentile, so z0.975. We can also do this more generally, and so we could say that we want to construct an interval that contains 1 minus alpha percent of the data. In that case, we have 1 minus alpha percent of the data in the center of the distribution, and then alpha percent of the data in the two tails. So on the left, alpha over 2%, and on the right, alpha over 2%. And so my quantiles, my percentiles, they will change from z0.025 and z0.975 to z of alpha over 2 and z of 1 minus alpha over 2. Furthermore, we know that z of alpha over 2 is minus z of 1 minus alpha over 2 because of the symmetry. This is clearly visible in the density function. So they are at the same distance from the origin because the one has alpha over 2% to the left and the other has alpha over 2% to the right. So z of alpha over 2 is equal to minus z of 1 minus alpha over 2. We have now obtained an interval which contains 95% of the data in case of a standard normal distribution. So this was the special case for a standard normal distribution because we used the letters z and we looked in this specific case. But we also know that we can transform any normal distribution into a standard normal distribution. So we can also apply the inverse transformation. To do this, we just replace z by x minus mu over sigma. And then we bring it back to an interval around x. And so, for any given normal distribution, the reference interval is the interval mu plus or minus sigma times z1 minus alpha over 2. So this is the reference interval. This is the interval that will contain for the given normal distribution 1 minus alpha percent of all the observations. However, in the reference interval, mu and sigma are unknown and we will have to estimate those. So we will estimate them using our sample and we replace the population mean by the sample mean. We replace the population standard deviation by the sample standard deviation. So as said, this is the reference interval or the normal interval. A reference interval is often used in clinical chemistry. So it will help you to compare a test result of a patient with a certain suspected pathology with the reference interval. So it will help you to decide whether or not the patient has this pathology, yes or no. How does it work? First, you obtain test results for healthy people. With the test results for the healthy people, you construct a 95% reference interval for healthy people. Then if you want to test a new person, you get a test result for that person and you compare it with the reference interval. Since you know that 95% of the data of healthy people would lie or should lie in the reference interval, you could say that if the test of this new person falls outside the interval, it is most likely that he is not healthy because his data, his test result is deviating from the reference interval of the healthy people, and so you are quite certain, you can be quite certain, or you have a strong indication that this person is not healthy. If it lies within the interval, then you have a strong indication that the person is healthy. So again, a reference interval is an interval that contains with a certain probability a random subject of the population. For a standard normal distribution, we know that with 95% probability, a random observation lies between the values minus 1.96 and plus 1.96. So you can look this up in your tables and then you will find that the 2.5 percentile is minus 1.96, the 97.5 percentile is 1.96. We can then generalize this to any random normally distributed data, and we can say that 95% lies within the interval mu plus or minus 1.96 times sigma. So here we have 1.96 times the standard deviation, which determines the width of the interval. Often the value here is rounded to 2, so we say that 95% lies within the interval mu plus or minus 2 times sigma. Furthermore, it can be shown that 68% of the data lies inside the interval mu plus or minus 1 times sigma, and 99% lies in the interval mu plus or minus 3 times sigma. This is called the 68, 95, 99% rule. So in summary, a distribution can be seen as a generalization of a bar plot in the discrete case or of a histogram in the continuous case, where we assume that we have an infinitely large sample, so the entire population. The distribution will describe how likely it is to observe a value or a range of values when drawing at random from the population. And similar to the sample, we define measures of location and measures of spread, but this time for the population, so we have a population mean and a population variance. These values are the values that would have been observed if the sample would be equal to the entire population. So if we have an infinite sample, if we then calculate the mean, we obtain the population mean. If we calculate the standard deviation, we obtain the population standard deviation. For the population, we use Greek letters to indicate location and spread. So the population mean is indicated by mu, the Greek letter for m. The population variance is indicated by sigma squared, where sigma is the Greek letter for s. Of course, these are theoretical concepts. We cannot observe them, we cannot measure them, we can only try to approximate them. And we estimate them then based on the sample. So the population cannot be observed with the mean mu variance sigma squared, will be estimated through the sample which we can observe with the sample mean and the sample standard deviation or the sample variance. So for the captopril example, we are here in the estimation. We estimate the effect of captopril in the population through the effect of captopril in the sample. So this is just a visualization of population versus sample. The population is a large number of subjects, objects, items that you are interested in, and you take a small portion out of it, and this will be the sample. So you take the small portion, then you measure or you observe for this small portion, for this sample, and then you try to generalize this to the entire population. As already said before, it is impossible to investigate the entire population, so we limit ourselves to the sample, and through this sample we try to estimate the population parameters. The population parameters are usually unknown, so we estimate them through the sample parameters. Small remark, an estimate is when you use the sample. If you are looking at the random variable, then you call it an estimator. So a random variable is an estimator. So if you have the random variable of the mean, it's the estimator. Otherwise, it is an estimate. So example, what we do is we use the sample mean to find the population mean. We use the sample standard deviation to find the population standard deviation. So we take our observations, our measurements. For example, the measurements we obtained for the sulfate concentration in rivers in the Catskill Mountains. And then we calculate the value for the sample mean. So small x bar is 1 over n times the sum of the xi's. And we calculate the standard deviation, the sample standard deviation, as 1 over n minus 1 times the sum of xi minus x bar squared. So again, what we said also in the previous chapter, here if we look at the standard deviation, you have n minus 1 instead of n, because you have this estimate that you already use in the calculation. So you made already one estimate to use in the calculation for another estimate. So what you have to do is you have to reduce the degrees of freedom by 1. And so instead of dividing by n, you divide by n minus 1. Within the same example, we could be looking for the probability to find concentrations between 60 and 70 micromolars per liter. So here in this case, we will apply the normal distribution to calculate the probability. We will assume that the data are normally distributed, but the population mean and the population standard deviation are unknown. We estimate them from the sample, so we get a sample mean of 61.92 and we get a sample standard deviation of 5.24. Then calculate the probability that x lies between 60 and 70. So the probability that x lies between 60 and 70 is the probability that x is smaller than 70 minus the probability that x is smaller than 60. What we then have to do is calculate these two probabilities. Let us start with the probability for x smaller than 70. The first thing we have to do is bring it back to a standard normal distribution. So we subtract the mean and we divide by the standard deviation. So we get phi of 70 minus 61.92 over 5.24, which is phi of 1.54. The next thing to do is look up this value in the table for the standard normal distribution. What you see here is part of the table from the course notes, and the table here gives you the values of phi of x. What we are looking for is phi of 1.54. So what you do is you first look in the first column for the first two digits, 1.5, and then in the first row you look for the second digit, which is 4. 1.54 will be on the cross section of 1.5 and 4. So what you do is move down in the column of 4 until you are at the row of 1.5, and then you see that the value that we are looking for is 0.9382. So the probability x smaller than 70 is 0.9382. In a similar way, you can calculate the probability that x is smaller than 60. This gives you a phi value of minus 0.37, and for this one you will find that the probability is 0.3557. The probability that we are looking for is the probability of x between 60 and 70. So we take the probability x smaller than 70, which is 0.9382, and we subtract the probability x smaller than 60, which was 0.3557. And the probability that we attain then is 0.5825. So the final answer is 0.5825 or 58.25%. We can then also calculate the reference interval for this concentration. 95% of the rivers in the Catskill Mountains is expected to have a sulfate concentration between which values. So the values that we are looking for are the endpoints of the reference interval. So the reference interval was mu plus or minus sigma times the percentile. In this case, we do not know mu and we do not know sigma, so we have to estimate them with the values from the sample. And so we use the sample mean, 61.92. We use the sample standard deviation, 5.24. And then the percentile, in this case the percentile is that of the 97.5%, because we have 2.5% on the left side, 2.5% on the right side. So the percentile value that we have to use is 1.96. If we then plug in these values, we see that the reference interval runs from 51.65 micromolar per liter up to 72.19 micromolar per liter. Clearly, everything that we have done so far depends on the assumption of normality. So we always assume that our data follow a normal distribution and we calculate as if they follow the normal distribution. But how can we verify this using the sample? So how can we use the sample to see if my data are really normally distributed? A first idea might be to use the histogram to check normality. However, often a histogram is not detailed enough to get a clear view on normality. Therefore, it is better to use a QQ plot. A QQ plot is a quantile plot. So on the one axis, you plot the theoretical quantiles, so the one that you would expect in theory. On the other axis, you plot the sample quantiles, so the ones that you get from your sample. And then if your distribution is the same as the theoretical distribution, then the points that you draw should be on a line. So on the x-axis are the theoretical quantiles of the distribution that you are looking at. In the case of a normal distribution, these will always be the quantiles for a standard normal distribution. On the y-axis are the sample quantiles, so the quantiles that you calculate from your sample, so the values that you find in the sample in such a way that a certain percent of the data is below that value. And so you will be comparing your sample quantiles with your theoretical quantiles. Remark, as I said, the theoretical quantiles are always the ones for a standard normal distribution, but you can be checking for any normal distribution. So if you would be checking a standard normal distribution with a standard normal distribution, then you would expect that the points that you draw, so the points that are plotted in the QQ plot, are on the first bisector, because they have to be the same. Your theoretical quantile has to be exactly the same as your sample quantile. If you are comparing your theoretical standard normal distribution with any other normal distribution, then you are only looking if they are on a line. Why does it still hold that they are on a line? Because again of the linear transformation property. Since you can bring back any normal distribution to a standard normal distribution, the sample quantiles will not be exactly the same, but if you plot the dots, they will still be on a straight line. One remark with the QQ plot. For the points at the end, so the ones in the tails, you have to be very careful. Here, because they are at the ends, at the tails of the distribution, there are usually very little observed data points in the sample. And so you have to use very little information to calculate these sample quantiles and to compare them with the theoretical quantiles. So there can be some deviations in the tails at the extremities of my QQ plot. So you always have to be a little bit careful with the end points, the final outside points in a QQ plot. Let us then take a look at how to read a QQ plot, or what can we see in a QQ plot. In the upper left QQ plot, we have a distribution which is right skewed. So what we see for a right skewed distribution is that there is a curve upwards away from the straight line. So both on the left side and on the right side, they go up away from the line. The plot on the upper right side, this is a left skewed distribution. So here we see the inverse. The left side and the right side, they go down away from the straight line. So they move, there's a curve downwards away from the straight line. The third plot is that of a long-tailed distribution. A long-tailed distribution is actually just a distribution where both the left tail and the right tail are heavier than the tails of a normal distribution. So you have a heavy tail on the left and on the right side. So what you see in this QQ plot is that it is a combination of the previous two. The QQ plot of a heavy-tailed distribution combines the right side of the QQ plot of a right-skewed distribution with the left side of the QQ plot of a left-skewed distribution. Why? Because in a right-skewed distribution, we have a heavy tail on the right side. So we see that here in the long-tailed, in the heavy-tailed distribution, we also observe this heavy right tail with points that move upwards on the right side. And a left-skewed distribution has a heavy left tail. And so in the long-tailed distribution on the left side, we see this also by the points which move downwards away from the straight line, which corresponds to the left tail, which is heavier in a left-skewed distribution. The fourth plot is the opposite. It is a short-tailed distribution. So it's a distribution where the tail on the left side and the tail on the right side is less heavy than the tail of normal distributions. In the fifth plot, we see a QQ plot for a bimodal distribution. A bimodal distribution is a distribution who has two modi, so it has two peaks if you draw the density function. What we see in this QQ plot is that we have sort of an S shape which passes 3 times the straight line. So here we have an indication for your first peak and an indication for your second peak. And then the sixth plot is a plot for rounded data points. You can see that the data are rounded because you have small intervals, small straight lines, instead of dots, instead of points. Why is this? Because they are rounded, you have multiple values which correspond to the percentile, to the sample quantile. So if we look at the QQ plot for cholesterol, what we see is that the left tail moves upwards and also the right tail moves upwards. This was an indication of a right-skewed distribution, which also corresponds to what we have seen in the histogram before. So the histogram is clearly right-skewed. The right tail is a lot heavier than the left tail. The red line on top, this gives the density function for a normal distribution. What we see in this is that on the left side, the tail of the normal distribution is heavier than the tail of my histogram. So on the left side, we have a short tail. And on the right side, we see that the tail of the histogram is higher, is heavier than the tail of the normal distribution. So we have a heavy right tail. So here we have a heavy right tail, a short left tail. So it is a right-skewed distribution. We corrected right skewedness before by taking a logarithm, and if we take the logarithm of the cholesterol, we see indeed that the data have become a lot more normal. If we look at the QQ plot, the data points seem to follow almost perfectly the straight line. Same thing for the histogram on the left side. The histogram and the theoretical normal distribution, they seem to correspond very well. Before we calculated the reference interval using the normal distribution and the normal values. There are also alternative methods which use the percentiles that we observe in the sample. So here what you do is you use the percentiles that you obtain from the sample. You only look at the sample and you do not look at any theoretical assumption that the data should be normally distributed. For example, assume that we have the cholesterol concentrations, then we know that 68% of the test subjects has a cholesterol concentration between the 16th and the 84th percentile. Why is this? 68% means that there is 32% on the outside of this interval, 32%, which means 16% on the left side and 16% on the right side. If we then look at the sample and we calculate the sample percentiles, we find that the reference interval, the 95% reference interval, is 14.8 up to 22.7. Similarly, you can also calculate the 95% interval, which will be between the 2.5% and the 97.5% percentile. And you get that 95% of the data in the sample lies between 12.4 and 27.8. What you can observe from these intervals is that the reference interval is no longer symmetrical, but is really based on the distribution of the data. The advantage of this method is that it does not need the assumption of normality. So you don't have to assume that the data are normally distributed. You don't have to make modifications if they are not normally distributed. You don't have to use your sample to see if they might be normally distributed. There is no need for all of this. Furthermore, it also does not rely on the variances, which are anyway inadequate for skewed data, because your variance only makes sense, only gives you a good idea of a distribution spread if the data are symmetrical. So the advantage is that it is a freer way to find the reference interval. The disadvantage is that extreme percentiles are very sensitive to outliers in small samples, and so it is possible to get reference intervals which will be enormously large. To conclude, if you know that your data are normal or approximately normal, it might be better to use the standard calculation of a reference interval. If you are facing skewed data or data which might be deviating from normality, the method using the percentiles in the sample might be a better option. Let's then move back to the cholesterol example. We saw that the cholesterol data are right skewed, and we applied a logarithmic transformation to the data in order to obtain more symmetric, more normally distributed data. So since they are log transformed, they are more symmetric, and in this case a standard deviation makes sense, and we can calculate a reference interval for these log transformed data. So 95% of the log transformed cholesterol concentration lies in the reference interval between 2.908 plus or minus 2 times 0.213. So 2.908 is my sample mean, 0.213 is my sample standard deviation, and I find a reference interval, a 95% reference interval, going from 2.49 up to 3.33. Since log transformed cholesterol concentrations don't really make sense in real life, we have to transform them back. And so we will take the exponential of both of the endpoints of the reference interval. So the exponential of 2.49, which gives me 12, and the exponential of 3.33, which gives me 28. And so my 95% reference interval for the cholesterol concentrations lies between 12.0 and 28.0 milligrams per centiliter. We then see that the result that we obtain this way is very similar to the interval based on the percentiles. Also here, the interval is not symmetrical, and the values are very close to the values that we obtained on the previous slide, namely 12.4 and 27.8. Remark that we had a pretty large sample of almost 4,000 observations, and so the estimate is quite accurate. If we have smaller sample sizes, the estimates will be less accurate, and so there might be bigger deviations between the reference intervals. So between the reference interval calculated using the normal definition of a reference interval and the reference interval using the percentiles. Some final remarks on reference intervals. These intervals, they use the estimated parameters as if they are known. So it's not entirely correct what we are doing. So they do not take the uncertainty on the estimation into account. So we have estimated our population parameter. There is uncertainty in the population parameter estimate. Because we use a sample, we don't have the exact value of the population parameter. We only have an estimate, so it's always less accurate than the true value. So there is uncertainty on how good this estimate is, and we have not yet taken that into account. So the intervals that we are showing are not correct. They will usually be too narrow because there is extra uncertainty through the estimate that has to be built into these intervals. Actually, the estimators x bar and s are random variables themselves because they vary from sample to sample. So for each sample, we might find or we will find a different value of x bar and s, and so there is variation on them. There is randomness on them. They are random variables. And so what we have to do is we have to study the properties of the sample mean x bar and also a little bit of the sample standard deviation s in order to correctly generalize the results from the sample to the entire population. So to build in the extra uncertainty in the intervals. And so what we will be doing in the next part is look at the sample mean x bar. The sample mean x bar is a random variable itself, so it has its own distribution, and then we will be studying the properties of this distribution of the sample mean. So we will be looking at what is the mean of the sample mean, what is the standard deviation of the sample mean, and how can we incorporate this to get better estimates of a reference interval to build in the uncertainty on the estimation.